Welcome to the deep dive, the place to come when, you really want to get to the bottom of, kind of the most exciting stuff out there.
Yeah.
And I think we've got some really cool stuff today. We're going to be talking about, how Earth's continents formed.
Yeah.
And some new research that's kind of challenging the traditional way of thinking about that.
Right.
I'm really fascinated by this.
Absolutely, yeah.
You and I, we've been kind of, digging into this paper in Nature, came out pretty recently. And, our mission today is to really unpack, what are the implications for our picture of early Earth?
Yeah.
And potentially, even thinking about other planets.
Yeah, for sure.
So... we should probably start with just what's the traditional explanation, right? Like, how did geologists always think that continental crust came to be?
Well, the way I always learned it was the sort of key player was plate tectonics. So the idea is you've got these plates moving around on the surface of the Earth, and in certain places, you get subduction zones,
right,
where one plate is diving under another. And the thought was that process, that sort of intense melting and chemical reactions, that's what created this sort of unique chemical fingerprint of continental crust.
Okay, so the idea is that this unique recipe of elements in continental crust kind of needed those subduction zones, right?
That's right. So the idea was, if you look at the composition of continental rocks, there's something really interesting about them.
Yep.
They're surprisingly low in a particular element called niobium.
Oh, okay.
And this is actually kind of a big deal in geology. We call it a negative niobium anomaly.
Oh, okay.
It's like a missing spice in a dish.
Okay, so the idea is that this unique recipe of elements in continental crust kind of needed those subduction zones, right?
That's right. So the idea was, if you look at the composition of continental rocks, there's something really interesting about them.
Okay.
They're surprisingly low in a particular element called niobium.
Oh, okay.
And this is actually kind of a big deal in geology. We call it a negative niobium anomaly.
Okay.
And for a long time, the thinking was that this negative niobium anomaly and that missing niobium, that was basically a result of this subduction process. So the idea was, as the ocean plate is sinking down into the mantle, there's all this melting going on, all these chemical reactions, and in that process, certain elements, including niobium, they behave in ways that lead to its removal.
So it gets pulled out during that process.
Exactly. So for a long time, if geologists found rocks that had this low niobium, this negative niobium anomaly,
right,
they would kind of point to that and say, aha, that's a sign of past subduction.
Right.
And that was kind of, seen as evidence for plate tectonics.
Gotcha. So, okay, so that's kind of the traditional, the textbook picture, right?
That's right.
And now this new research is kind of throwing a wrench into that, right?
It really is. Yeah, it's really exciting because it's challenging this whole assumption that we need plate tectonics to create that unique continental crust.
So tell me about the study. Like, who are the folks behind it?
Well, the lead author is a Professor Emeritus Simon Turner,
okay,
from Macquarie University.
Okay.
And he's working with a team of researchers from Australia, the UK, and France.
Okay, nice. Global collaboration.
Yeah. It's a big international effort.
Very cool.
And their findings are really quite remarkable.
And this was published in Nature, right?
That's right, yeah. It just came out April 2nd, 2025.
Okay.
And what they're basically arguing is that very first crust on Earth,
okay,
the protocrust,
mm-hmm,
which formed, over 4.5 billion years ago.
Yeah.
Wow. It already had these chemical traits, including that low niobium signature that we typically associate with continents.
Okay.
And this is really kind of mind-blowing because it means that key chemical feature.
Yeah.
It wasn't something that slowly developed because of plate tectonics.
Yeah.
But it was there almost from the get-go.
Wow. So it kind of rewinds the timelines.
It really does.
Yeah.
It really does. It's a huge shift in how we've been thinking about our planet's early history.
Yeah. So what's the central mind-blowing revelation here? Like, what's the aha moment in all of this?
The big aha is that these defining chemical characteristics, most notably that lack of niobium.
Okay.
They seem to have been baked into the Earth's very initial crust, the protocrust,
Yeah.
during this period called the Hadean Eon,
Right.
which was basically the first 500 million years or so of Earth's history.
Right.
And here's the kicker: this was before we think plate tectonics, at least as we recognize it today, really got going.
So it predates that whole system that we kind of always associate it with.
That's right. So the aha here isn't just how niobium got depleted,
Yeah.
but that this fundamental continental fingerprint, it might predate plate tectonics by hundreds of millions of years.
Wow.
And that's a big deal.
That's huge. Okay, so wait a second. How could this happen without plate tectonics?
That's the $1 million question.
Right. Like that's the thing that jumps out.
Right.
So paint us a picture of early Earth. What were the conditions like, and how could this chemical signature have emerged in that environment?
Well, it was a pretty wild place. I mean, we were talking about a planet that had just formed, still incredibly hot.
Okay.
And what you had was essentially a global ocean of molten rock.
The magma ocean.
A magma ocean, exactly.
Yeah.
And during this period, Earth's dense iron, it was sinking to the center to form the core.
Right.
And what the researchers did was they used really sophisticated computer simulations to recreate these extreme conditions.
Okay.
And what they found was really fascinating. Under those intense temperatures,
Okay.
and crucially, the chemically reducing environment of early Earth, niobium would have behaved in a way that we just don't see today.
Okay. So reducing environment, what does that mean?
Yeah, it's a good question. It's a little bit of a technical term, but basically, today Earth's upper mantle, it's relatively oxidized.
Okay.
Which basically means that elements like to combine with oxygen.
Right.
Early Earth, before we had a substantial atmosphere,
Right.
it was more reducing, meaning there was much less free oxygen around.
Gotcha. Okay. So under those conditions, how did niobium behave differently?
Well, what the simulation showed was that in those oxygen-poor conditions, niobium would have been siderophilic.
Yeah. Okay. Siderophilic?
Yeah.
That's a new word for me.
It's a good one.
What does that mean?
It basically means metal loving.
Metal loving. Okay.
Yeah. So basically, niobium would have been much more attracted to the molten iron
Okay.
that was sinking down to form the core.
Oh, I see. So instead of sort of sticking around in the rocky mantle where it could, eventually be incorporated into the crust,
Right.
It's kind of hitching a ride
Exactly.
on that iron express down to the core.
Yeah. It's like you hopped on a train and went straight to the center of the Earth.
That's a great way to put it. Okay, so basically what you're saying is that during that initial separation
Right.
of the Earth into its layers,
Right.
the niobium was being pulled out of the material that would eventually become the crust.
Exactly.
Right. It was just gone.
Exactly. So if you're pulling the niobium out, during that early stage, then the remaining mantle, the stuff that the first crust solidified from, it's already going to be low in niobium.
Okay, that makes sense. It's like you're making a cake and you just deliberately leave out an ingredient.
Right.
It's not going to magically appear later.
Exactly. It's like that missing spice, right?
Right.
That we were talking about.
Yeah. Okay, so this negative niobium anomaly, the signature that's in continental rocks, it's not necessarily the result of billions of years of subduction.
Right.
It could be like a relic of that very early process.
That's right. It's like a fingerprint from the Earth's infancy.
Wow, that's a pretty profound shift in perspective.
It really is.
And it would kind of neatly explain why we see that low niobium in almost all continental rocks, no matter how old they are.
Exactly. And this is one of the things that Professor Turner and his team really emphasize.
Okay.
Is that, if this chemical signature was already there,
Yeah.
because of core formation, then finding these low niobium rocks, it doesn't necessarily tell us about plate tectonics.
Right.
It might not signal the beginning of subduction at all.
Oh, I see. So it's like we've been using the wrong signal.
It could be. Yeah. It's like we've been looking for the wrong clue.
Right.
Yeah.
Okay. So if this early protocrust already had this this continental chemical makeup.
Yeah.
What ultimately happened to it? I mean, the Earth today doesn't look anything like a uniform layer of primordial crust, right?
No, definitely not. This early protocrust, it went through a lot.
Okay.
I mean, we're talking about the Hadean eon,
Right.
which was a time of intense bombardment by meteorites.
Yeah.
There's also evidence that suggests there were periods of really significant crustal recycling, perhaps through processes like crustal peeling.
Okay.
Where large slabs of that early crust actually delaminated and sank back down into the mantle.
Wow.
And then, of course, eventually plate tectonics, as we know it did get going.
Okay.
Although, probably in a more intermittent fashion at first.
Right.
So all of these processes, they would have really reshaped and chemically modified that initial crust.
Right.
And one of the important things is that it's thought that this early crust also became enriched in silica through these impact events and other interactions with the mantle.
So it was a really violent and transformative early Earth.
Absolutely.
Like this first crust probably wasn't, just a solid, unbroken shell. It was probably pretty fractured and constantly evolving.
Yeah, more like a patchwork quilt, of different types of rocks constantly being reshaped and modified.
Okay. You mentioned the possibility of plate tectonics operating in fits and starts early on.
Right.
Can you unpack that a little bit?
Yeah, so the early Earth was an incredibly energetic environment.
Okay.
You had these massive impacts from meteorites.
Right.
And all that energy, it could have triggered localized episodes of subduction.
Oh, okay.
Or other forms of tectonic activity.
So like little bursts.
Exactly. Like little bursts of activity here and there.
Okay.
But it's unlikely that it was this globally coherent, self-sustaining system that we see today.
Right.
And most researchers, including Professor Turner and his team, they think that sustained widespread plate tectonics probably didn't really get going until around 3.8 billion years ago.
Gotcha. Okay, so basically the ingredients for continents were there almost from the beginning, but the sort of geological forces that sculpted them
into the land masses we know today,
that took a lot longer and it was a lot more complex.
That's right.
That's really cool. So what are the broader implications of all this? Like, does it just change how we think about our own planet?
Well, it certainly does that.
Okay.
But it actually goes even further than that.
Okay.
Because this research, it offers a new perspective on how continents might form on other rocky planets.
Ooh.
Throughout the galaxy.
You're getting good. Okay.
Yeah, it's pretty mind-blowing. So if that fundamental chemical signature of continental crust, that low niobium, if that could arise naturally, just as a consequence of planetary formation and core differentiation, without the need for plate tectonics, then it suggests that the building blocks for continental light crust might be a lot more common on young, hot, rocky exoplanets than we previously thought.
Oh, wow.
Yeah, so it's really exciting because it gives us a new framework for thinking about, the potential for early crustal development.
Yeah.
And even, maybe the long-term geological evolution of planets around other stars.
So it kind of changes our search parameters.
Exactly. It means that, when we're looking for these potentially habitable planets that might have continents, we don't necessarily need to see evidence of active plate tectonics as a prerequisite.
Oh, that's huge.
Yeah.
Okay, so just to kind of sum up the key takeaway here.
Yeah.
It seems like what we're learning is that Earth's continents may have had that defining chemical characteristic.
Yeah.
That lack of niobium.
Right
from the get-go.
Exactly.
And it's basically an inheritance from the processes of core formation.
Right.
Back in that primordial magma ocean.
That's right.
And it's totally separate from the development of plate tectonics.
Exactly. It's a fundamental shift in our understanding of Earth's early early geological processes.
Yeah, and it kind of highlights the importance of that initial differentiation
Right.
of the planet
Absolutely.
in setting the stage for continents to form.
Yeah, it's a really profound realization.
Yeah, I'm kind of blown away by all this.
Yeah, it's really cool stuff.
It really is. It really makes you think, right? Like if these building blocks of continents
Yeah.
arose so early,
Yeah.
and it seems like almost as a natural consequence of planetary formation.
Yeah.
Like what other fundamental things about planetary evolution might we need to rethink?
Right.
You know, and what does this mean for other worlds? Like
Yes.
what does it mean for the potential for other planets to develop, you know, similar kinds of crust? Right.
And maybe even the long-term habitability of those worlds.
Yeah, absolutely. It's really a whole new way of thinking about planets.
It really is.
Yeah.
Well, this has been a fantastic deep dive.
Yeah, it has.
I'm so glad we got to dig into this together.
Me too.
Thanks for joining us.
It's been a pleasure.
And we'll catch you next time for another deep dive beneath the surface.
Sounds good.